This quick, crazy lesson is going to be horrible with drawings, but please keep in mind I'm trying to draw on my like laptop mouse pad. So these are not going to be beautiful, but it'll serve its purpose. Okay, so today we are going to talk about the difference between thermal energy and temperature and what is different about what's going on with your molecules and like how do we come up with these things. Okay, so there's a really good video that looks like it's from like 1940 or something, but it actually does a great job of comparing the difference between the two. So I have kept it in my slides and it's on our grid, our learning grid. And then there's another one where a guy is talking about a coffee mug versus a swimming pool and the molecules in it, and how that is also a great comparison of thermal energy and temperature. So check out those two videos if you have not yet. And then make sure that you watch this as well, because I kind of do the same thing, but I just draw it out. So first of all, I want you to think of the fact that what I'm going to explain today is not really going to be on a scientific level. Okay, so I like to think of things in a way where I can relate to them. Okay, so I'm going to talk about molecules, and those molecules are kind of like the kinetic sand of Earth, right? So the more if you're trying to build a model of a coffee mug, right, with coffee in it, how much kinetic sand would you need in order to make that, right? You can think of Play-Doh too, but kinetic sand has those little tiny little spheres in it, kind of like molecules. So that's what I'm going to say. So I'm going to try to see if I can actually find these. Nope. All right, so I'll just freehand this. Okay, so if we have a coffee mug, right? Again, I'm using this with my little tiny fingers, so this is gonna be about as derpy as it gets. But okay, so we have this tiny little coffee mug, right? How much kinetic sand would it take to make it? Not too much, right? And think about how many total teeny tiny spheres would be in that coffee mug. Okay. And then think about, I would also like to build a model of a swimming pool, correct? How many spoonfuls or chunks or balls would it take of kinetic sand? Okay. So obviously not to scale. This is just because it's all that can fit on my screen, right? But here's our swimming pool, right? And it's filled with water. How much kinetic sand would be in there? So again, like I said, this is definitely not true scientific terms, but it's enough to give us a hint of what's going on. So I'm going to say in the pool that there are, these are going to be the molecules that fill up the pool, correct? Okay. So we're going to say in total, there are 10,000 molecules in the pool. Okay. That's a lot of molecules, correct? And then in our lovely little coffee mug over here, we're going to say that the coffee mug has a total of 3. Okay, not a lot in comparison to the pool, right? But if you think about it, like how many cups of coffee would it take to fill your swimming pool? A lot. Okay, so to say that we have 3 in the coffee mug and 10,000 in our pool, I'm going to go with that. Okay, so again, not scientific, but this is how I wrap my brain around things. Okay. We're going to talk about the amount of energy in the molecules in terms of miles per hour. Okay. Because that's something kids can wrap their brains around, and so can I. Okay. So for these molecules in the coffee mug, I literally just took the coffee off of the coffee pot, like maker. So it's super, super, super hot. Okay. These molecules are vibrating crazy fast. Okay. If they were cars on the highway, okay, for easy math purposes as well, how fast would a crazy fast car be on the highway? Okay. Um, some of my kids in the past have been like 500 miles an hour. Okay, so we're going to go with that. All right. So 500 miles per hour is how fast each of those molecules is going, correct? So 500 miles, 500 miles, and the third one was also going 500 miles per hour. Sweet. Okay. So all together, if I was going to add up all the energy in those molecules, what's the total energy? We would say 1,500 miles per hour. Cool. That's the total. Total. Yes, yes. Okay. So if that's my total, Now I want to look over at the molecules in the pool, right? There's 10,000 of them. To fill my pool, I took the hose from my house and I filled it with my pool. Okay. So that water, if you've ever been in it, especially at the end or the beginning of summer, really cold water. Okay. It feels like an ice cube. So if those molecules are super cold, what's the thermal energy level? What's the vibration level there? They're barely moving at all. Okay. Not a lot of energy. They're really, really slow. So I've asked my kids in the past, if you're on the highway, what's a very slow car? What's like the slowest a car could drive? Okay. And my kids have said, oh, well, let's just make it easy. We're going to say each of those molecules is driving, I'm going to make this so it shows up, 1 mile per hour. Okay. I'm not even sure your car will register that on the speedometer. Okay. So they're only going 1 mile per hour. Really slow. Okay. How many molecules are there? There were 10,000, right? 10,000 molecules, barely moving at all, right? But if I take that 10,000 molecule and I multiply it by the speed of each molecule, okay? Or I just say, I'm gonna add them all together. 1 mile per hour plus 1 mile per hour plus 1 mile per hour plus 1 mile per hour. And I do that 10,000 times, okay? How many miles per hour I'm going to have total, right? What's the total going to be? It's going to be 10,000, okay? So even though my molecules are barely moving at all, because there's so many of them, when I add all that together, it equals a freakishly large amount, right? They're super, super cool, but there's so many of them that the total is really high. Okay. And then you look over at that coffee again, right? Those things are going crazy fast, scary, scary fast. But there's only 3 of them. So when you add them all together, it only equals 1,500, which is nothing in comparison to the 10,000, right? So when we talk about this thermal energy, okay, thermal energy is this. Thermal energy is the total, you need to repeat that with me, total. And again, I look really derpy. I swear my handwriting is better than that. But okay, so thermal energy is the total. It's taking a look at how many molecules there are and adding all of their speeds together. Okay. Temperature is going to be totally different. If I say, hey, look at the coffee mug, look at the pool, which one has the higher temperature? Right off the bat, I mean, little teeny tiny kids can answer that, right? The coffee's hotter. It has a higher temperature. You should know that off the bat. It's not a trick question, okay? But why? Why? Okay? So that's the next thing that I want to do. Ta-da! Okay, so this is going to be really challenging. Please bear with me on this one. Okay, so here is, that's my head. This is my hand and my leg and my foot, my other leg and my foot, my body, waving hello with my other hand and finish out the head. Okay, so here's my body, right? Okay, so we are going to use the outline of my body to figure out what's my thermal energy and my temperature. Again, is this very scientific? No, it's not going to be, but it's going to help you wrap your brain around it, I promise. Okay. So I'm going to first talk to you about the fact that, hey, if you go and if you touch your forehead, you touch your neck, even if you touch your torso, those are usually pretty warm, okay, in comparison to your appendages, right? Your fingers and your toes. Like if you ever go out on a cold day, those things cool off a lot quicker, right? Those are the first ones to get cold. So just in general, where your blood is pumping the fastest and is closer to your heart, the warmer you're going to be. Okay. So if I'm trying to tell the temperature or the speed that my molecules are shaking, those molecules that are in my head, this is not my eyeball, these are my molecules. Okay. Okay. So if I have some molecules in my head and in my neck and in my torso, right? Those are my molecules. Those are going to be moving pretty fast because those stay warm, right? But the further I get out to my fingers and my toes, those molecules don't move as fast, right? They don't move as fast. They usually are cooler than the rest of your body, especially if you're outside on a cold day. Okay. So I'm pointing this out. When we say, hey, I took my temperature and it says 101, does that mean every single molecule in your body is 101 degrees? No, it doesn't. What it means is it's your average, okay? Because remember what we just said. If I took the temperature of your forehead molecules, right? And the speed, if I could look at them, the speed is a lot faster. Their energy is a lot higher than the speed in my fingers and in my toes, okay? Right now, my toes are freezing, okay? And I can't kind of feel my nose. It's pretty cold in here. Okay, so those molecules are totally different. All right. So because of that fun fact, I'm going to go through and I am going to put the speed. Okay, so I'm going to say just for easy math purposes, right? Each of the molecules in my like my head and my torso and my neck area are moving again at 100 miles per hour. Do we calculate the speed of molecules in miles per hour? No, we do not. That is not a scientific way of doing it. Why am I doing it? Because it's really easy and it's relatable. Okay. We need to make math relatable. We need to make science relatable. Okay. So those molecules are moving really fast. Okay. They're fast cars. Okay. And then the molecules in my fingers and in my toes, not moving as fast, right? So for easy math again, I'm going to say these molecules are shaking at a speed of 50 miles per hour. Okay. Yeah. Okay. So if I were to say, what is the thermal energy in my body right now? Do I only have like how many molecules do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. In real life, do I have 9 molecules in my body? Only 9 molecules? No. Okay, no. But again, this is a good visual. So I have 9 molecules in this picture. What is my total amount of energy in my body? Because that is going to give me my thermal energy. I'm looking for the total. Okay. So I have to add it all together. 100, 200, 300, 400, 500, 600, 700. So if I add all of this stuff together, I end up with 700 as my total amount of energy. Okay. Now, temperature is different. Temperature is an average. And depending on where we are in the school year and just in general, your like comfort level with math, you may or may have not practiced with average. Okay. Especially since we don't do like A, B, C, D grading anymore. Average isn't something that you're quite as used to. Kids used to be able to find that all the time with their grades. So, an average means in math that you are adding everything together, right? So we added them all together already, right? We added our energy together and we got 700, right? But in order to find the average, you take your total and you divide it by however many things there are. Okay. So I'm going to divide by however many molecules I have. How many molecules did we say we had? We have 1, 2, 3, 4, 5, 6, 7, 8, 9 molecules, right? 9 molecules altogether. Okay. So if I go through, if I'm trying to find this, my handy dandy telephone, right? My cell phone, I'm going to take 700 and I'm dividing it by 9, right? My total or my average is now going to be, what the heck? What do I do with that? Can you even see that? This usually freaks kids out, okay? If it's temperature, if you know anything about like when you take your temperature with a thermometer, usually you only say like 1 digit after, right? The nurse is not going to be like, whew, you have a temperature of 77.777777778. It's not normal, right? So for this, they would probably say, not that this is realistic. You should not. I don't even know if you'd be alive if you had a temperature this low. I'm not going to lie. I don't know much about that. But I'm going to round this. So this is 77.8. We're usually at, what is it, 98.6 is what's supposed to be like normal and healthy without a fever. Okay. So anywho, this lets you know, hey, if I stuck a thermometer in my mouth and I only had 9 molecules, I stuck the thermometer in my mouth, basically it's like scanning my body. It's figuring out the speed of every molecule in my body, and it's totaling it all together. And then it's going to divide by however many molecules I have, right? So think about in general, if you stuck a thermometer in your mouth and all it did was give you your total, you would have like, I mean, I don't know, I haven't Googled it or anything, but you probably have like billions maybe. Okay. Your temperature is not going to be that high. You know that, right? You obviously know that. So think about it when you're trying to remember what's the difference between thermal energy and average, or thermal energy and temperature. If you go to take your temperature, are you going to have a crazy, stupid large number? No. Okay. So if you are given a crazy, stupid large number, you know that's just representing the thermal energy because that's your total amount. That's based on how many molecules you have, which is a crazy amount, right? That's your total. And then your temperature is going to be very low key because you are taking that crazy large number and you're dividing by how many molecules there are. Okay. So now think back to the difference between our swimming pool and our coffee mug, right? So the thermal energy was affected by how big it was, right? The coffee mug hardly had any molecules in it, right? Yeah. So this coffee mug only had like 3 molecules in it, right? Versus the swimming pool that is gigantic, right? In comparison. Okay. All right. So if you are trying to find your total thermal energy, right? The smaller the object, the lower the thermal energy because it hardly has any molecules in it, right? Thermal energy is going to be higher in something that has more mass. Have you heard of mass before? More mass, more stuff, right? It's made of more stuff. And if it has more mass, it means it has more molecules, right? You have more things to total together. So when we talk about thermal energy, the more the molecules there are in an object, the higher the thermal energy, right? Temperature is not going to be affected by that because once you divide it by however many objects are in there, it doesn't matter anymore. Think about, this is the other example I gave. Like if you lit a match, you can't even see this. Okay. Let's see if I can maybe choose a different color. This is supposed to be like a flame. I don't know if you can even tell or not. Okay. This is my flame. Okay. So there's a flame right there. And okay, there's the flame. And then we're gonna say, here is a huge bonfire. These are the logs, okay. Lovely logs here. And whoosh, there's our flame. Okay, I love it. This is just so believable. It's beautiful. Okay, so huge, huge, huge fire going on here, right? Okay. Which one has the higher temperature? Technically, they're both going to be about the same. They're both just flames, right? I mean, they're just flames started with wood. Okay. In general, unless you like used an accelerant like gasoline or something like that, they should be around the same temperature. They're both super, super hot. Okay. However, if I ask what's the difference between thermal energy, this huge bonfire is going to have a higher thermal energy. Why? Because it's bigger, more mass. The bigger it is, the more molecules it has. The more molecules it has, the higher total when you're adding all the energy together. Okay, so these would have roughly the same temperature, but thermal energy would be higher because it's more molecules in this one. Okay, so in general, that's it. Thermal energy is your total amount of energy. Temperature is going to be taking that total and dividing by how many molecules there are. So size does not matter on temperature whatsoever. Thermal energy, the bigger something is, the higher the thermal energy it's going to have because it's your